All right, I'm trying to keep my videos to 10 minutes or less, so that I did not answer part B of number 48, but the approach would be similar to what we did for 48 part A. You know the snow is level and it has the same coefficient of friction. You're trying to find how far the ski will travel along that level, and you're supposed to use energy methods. For 48 part B, you would use the known V2 at the bottom of the hill to talk about the kinetic energy of the ski at that point. You would say it's going to travel until it stops, so V3 will be 0, and the reason it comes to a stop is the work done by friction. So I would say that the kinetic energy at point 2 has to be equal to the work done by friction from 2 to 3. The kinetic energy at point 2, half mv2 squared, this is what you found in part A, is equal to mu sub k times normal force. And of course now we're at the level, so normal force is equal to weight, mu sub k, oops, I forgot the d there, times mg times d. And so again, the mass factors out, we don't know the mass. You solve for d this time, knowing mu sub k, g is 9.8 meters per second squared, and you, from part A, knew the velocity of the ski at point 2, which is the bottom of the hill. Let's at least set up number 51, a variation of the same. So problem 51 has a skier traveling at 11 meters per second, reaching the foot of a hill. So this time I know V2. And the skier is approaching an upward hill of 19 degrees. Skier glides 15 meters up the hill before coming to rest. So now V1, I called this V2, whatever, we'll call this V3, is equal to 0. Coming to rest, what was the average coefficient of kinetic friction? So mu sub k is now what's not known. We're going to apply exactly the same idea that we did for 48 to say that the energy at point 2 is equal to the energy at point 3. 2 and 3 just because I should have called it 1 and 2, but didn't. So I have kinetic energy at 2, gravitational potential energy at point 2. I have work done by friction happening the whole time. So these aren't actually true until I account for the work done by friction, plus kinetic energy at point 3 and the gravitational potential energy at point 3. So same argument as per usual. We'll say that the ground level is 0, y equals 0. We'll say that the kinetic energy at the top is 0 because we're told that it comes to a stop. I start piecing out what I know. Half m times v2 squared. v2 is known. Mu sub k times normal force times the distance going up the hill. So again, that's 15 plus mgy. We have the same issue as before, knowing the length of the hill rather than the height of the hill, or y of the hill, so we'll have to piece that out. And again, it's on an incline, so we need to use the y component of g in the tilted axes. So you basically are doing exactly the same problem, except this time you know the distance, you can find the vertical drop, you know the velocity, and you're solving for the coefficient of kinetic friction. Let's move on now to power. So my example problems for power are 57 and 60 of chapter 6. Flip to power. So the idea for power is that it's often quite useful to know, oops, I need to go over here, often quite useful to know not just the energy exchanged or the energy transformed, but it's useful to know how quickly that energy is exchanged or transformed. So our definition for power, at least for average power, is the rate of change of energy. And the work energy principle says that we can exchange work for rate of change of energy, so we can also express this as work per time. So we have two options for power. Then finally, if we write work as force times distance, distance divided by time is velocity, so we can also consider this to be force times velocity, but we're only considering the component of force that's parallel to the velocity, and we're only really considering average power. If we wanted to know instantaneous power, we would have to consider the instantaneous rate of change of energy. You're hearing this argument over and over again. So for number 57, How long will it take a 2,750 watt motor to lift, so this is the motor, to lift a 385 kilogram piano to a 6-story window that's 16.0 meters above. So the delta Y is 16.0 meters. The mass of the piano is 385 kilograms. This little bit of information tells me enough to know the work done to lift the piano. Or we could think of it as the change in gravitational potential energy of the piano. Either way, we're going to get the same answer, right? The work done is the weight of the piano times the displacement in the vertical direction. The change in gravitational potential energy is the weight times the change in vertical height. So 385 kilograms times 9.8 meters per second squared times the increase in y, 16 meters. I will have a change in gravitational potential energy / work done in lifting the piano of 60,368 joules. Then I know that power is equal to the rate of change of energy, or the work done per time. I'm trying to find the time, so I know the work done is 2750 watts is a joule per second. I have 60,368 joules, and I'm trying to find the time interval. Last step, time interval is 21.952 seconds. I might as well call it 22.0 seconds. Close enough. 22 seconds to lift the 385 kilogram piano to the 6th floor, which is 16 meters above the ground. I'm checking my time, aiming for 10-minute videos. I have 4 minutes left. So let's look at number 60. If a car generates 18 horsepower, so horsepower is the British or US unit for power, when traveling at a steady 95 kilometers per hour, what must be the average force exerted on the car due to friction? So I have a power measurement in funky units. I have a velocity in also slightly funky units, not meters per second. And I want to know the force needed to maintain that steady velocity, aka the force needed, or the force that is exerted by friction causing that velocity to be steady. So the idea here is to consider work as force times velocity. The force is exactly anti-parallel to the velocity of the car, so we don't have to worry about the parallel component. And the rest of this problem is really units issues. So I frankly Google horsepowers to watts, because I sure don't remember the conversion factor off the top of my head. 1 horsepower is 745.7 watts. So 18 horsepowers, the power of 18 horses is 13,422.6 watts. We're trying to find that force, the velocity, and again, frankly, I'm too lazy, so I am Googling kilometers per hour to meters per second. It's not a complicated conversion, I'm just lazy on a Saturday morning. So there are 0.278 meters per second per kilometer per hour. So 95 kilometers per hour is 26.38889 meters per second. And then finally the force is equal to work divided by velocity. I'm calculating. Oh, I guess wow, heck. I should be using my calculator, not my phone. 13,422.6 watts divided by 26.39 meters per second is a force of 508.6. Let's call it 509 newtons. So the force required for the engine to keep the car moving at a steady rate is 509 newtons, and that's equal to the force of friction required, or the force of friction on the car, keeping the car at a steady rate. So my intent here was to deal with a little conversion factor business with power. So, oops, I wrote that as work. That's power. So conversions for power, horsepowers versus watts. And then at least one example of using, oh my gosh, I wrote that as work also. That's power. Also using the power force velocity equation rather than the change in energy versus time. The end.